floor's
Yeah,
yours, Mark.
thank you, Di, for welcoming us to your place. Many years ago, in the early 70s, I had a flat in Peterborough Street. And so I was a graduate of Canterbury University, and Mike is a very recent graduate, having just completed his doctorate. And Andy mentioned his work on post-tensioned multi-storey timber buildings. But not being a geotechnical engineer, I've brought a Geotek man, Simon Woodward, who's principal of Geotek Limited in Auckland. He's an Auckland engineering graduate, so I've got 2 Canterbury and 1 Auckland. And I've brought John Reelick, and he's the principal and director of Tuakau Timber Treatment. Now, John is also a graduate of Auckland Engineering School, so we're not parochial at all. We've got a nice balance here. And John's particular expertise is in round timber, in treating round timber and processing it, and in piling. So he has a lot of experience in that area. So what we're hoping to do is just introduce you to maybe some new ideas, some new ways perhaps of doing things in timber. Now this is I was here shortly after the February earthquake, and among other things I saw this building, and I've been a timber design consultant for a few decades now, and one of the things about timber is that it's generally governed by stiffness, not by strength. So in a situation like this, we can see the resilience of that timber. Clearly it hasn't broken. It's got no actually visible means of support, so it seems to be still hanging up there while everything else has been pulled out from under it. So there's quite a reserve of strength in timber design. And this is Mike's work. You saw Andy showed that picture in the Canterbury laboratory. And so these sorts of structures can be designed not just to avoid loss of life, but to be very resilient and potentially quite a saving in financial loss, which is clearly a significant issue in Christchurch. And also, if you know anything about timber, you know when it's broken. There's no question about whether it's still fully competent or not. If it's broken, it's broken. And so you can then do something about that, either with some sort of a reinforcing system over the broken part, or even with epoxy or a proper adhesive grouting. So repair is relatively easily done if necessary. The building on the right, the Oddlands building, is a fairly early example of a large timber elements in a construction in Petone, but that relies again on reinforced concrete, major internal structure, and the timber is essentially just post and beam hanging off that central concrete core. And on the left we have a more recent project in Wellington, which is the structural system is typically sort of stick framing with plywood. And at this point we'll move on to some of the work that Michael has been doing. Michael joined me in Auckland middle of last year, and we've been working on utilising his sort of cutting edge knowledge in post-tension timber systems. And with a few grey hairs I've got hopefully some guidance on practical detailing, and together we've come up with some systems that we hope you might find interesting and maybe inspirational. So Michael, if I could hand to you.
Di, do I need the mic or?
Yes.
Okay. Right,
It's being recorded. We recorded today. I recorded today, and Jeff was helped by Tara recording tonight.
Rightio. So as Mark kindly introduced, I'm going to discuss a little bit about multi-storey timber building systems around the world, but also what we're proposing and recommending for Christchurch for our unique environment here. So in Europe, multi-storey timber buildings aren't really anything new. They've been around for a few years now, and they've been pushing the limits of how high they're building these structures. Now this one on the left was built in London, and that was 9 stories. It may not look like a timber building, but they've clad it to make it look like a steel structure, so that they don't actually advocate or advertise the fact that it's timber underneath. Anyway, They had a lot of benefits out of that construction, the construction of that building, such as the buildability of it, how quickly it went up, and for us in New Zealand there may be some seismic performance benefits, which is what they were investigating on the right hand side there under the SOFI project. Now that's on the Japanese shake table, E-Defence. It's a full scale shake table, and that's a full scale building that's been tested on it. So they've put it through the throes in terms of the Japanese seismicity, and they've come out with fairly good performance. In that particular building they found that in the top levels you sort of get a fishing rod effect where it flings you around a bit, so the accelerations can be a bit high, but we've figured out ways that we can deal with those issues. Oops, too fast. Just a little bit about North America. They're into light timber frame construction, similar to what we use for 1 or 2 story buildings in New Zealand. They're pushing the envelope on how high they can do that in multi-story construction, and instead of plywood or jib, obviously they use OSB, orientated strand board, but the concept's relatively similar. They've done their own earthquake testing, again on the E-Defence shake table over in Japan, and they've put it through its throes, and they've found that it's had a very good performance as well. So what we're proposing for New Zealand is it's tailored really to the commercial building market, so large open plans, something that might be appropriate for an office building. It's made out of solid timber, and I'll talk a little bit more about that in a second, what sort of solid timber you can make it from. And the key points about this construction systems are that it's rapid to build, so we can get many of these buildings up quickly if we need to. The fire performance of them is good. It's just like having a large log in the fire. It's going to take a very long time to burn, and you can predict how quickly that's going to burn. So you can get an idea of how many hours you'd have in this building to get out safely. It's lightweight, which has an impact on the foundations, which is really the key point of why I'm talking about timber buildings here, is the impact on the foundations. And it has high structural and seismic, specifically seismic performance as well. So I've looked at that in detail as part of my PhD research at the University of Canterbury, and we've taken this structure that we've designed here up in Auckland in our office, and we've subjected that to multiple earthquake records that are compatible with the events that you got here in Christchurch. So we put 15 earthquakes, various records that were recorded around the CBD site, and we've put those through the building, and ones that are spectrum, what we call spectrum compatible, which basically match the earthquakes that we have here. So what I'm going to show here is very quickly, if you'll allow me, a quick video of how it works. So it's a component-based system, so prefabricated modular components, and they're connected by these steel rods, similar to what Andy was talking about earlier. But we've designed it in a way so that at each level you have a joint between the prefabricated elements, and those work like a sort of seismic isolation at multiple levels. And what that does is it reduces the accelerations or the forces that you feel when you're up in those buildings at those levels. So it deals with some of those issues that I was alluding to for the CLT building earlier. Incidentally, CLT stands for cross-laminated timber. I forgot to tell you that before. So it's like a large version of plywood. But this system for New Zealand, we're looking at material alternatives, so all sorts of engineered wood product. And I mean, upon analysing these with all those 15 earthquake records, we are guaranteeing, or we're satisfying ourselves with the earthquakes that we put through, that this building is going to reach a good serviceability performance, so it's not going to shake around too much and make you seasick inside, but also under those really punchy ultimate limit state events, large earthquakes, is going to be able to accommodate that motion and deform. So enough of that. And these are the different sorts of timbers that we've designed for this sort of building system. So the one down the bottom is using glulam, and there's that CLT again, cross-laminated timber. Now there's a new outfit in Nelson that's just starting to produce this, that are coming online in April. So we'll be able to use that engineered product as well. It's prevalent all around Europe and in North America as well. There's LVL, which is laminated veneer lumber, 3mm laminations, just like plywood, that run all in one direction. So it's very strong and consistent. And then we've designed engineered commercial buildings using round timbers. which is a new way of thinking for commercial structures, which is, I believe, a very cost-efficient solution. So why would we use multi-storey timber buildings? Well, there's a whole myriad of reasons to go down that road, and I'm not going to go into detail here. I'll just mention that it is a national commodity, and why not use something that we produce? But the key thing that I'm going to focus on is that there's reduced mass in these structures. So what that means is that you have reduced seismic demands on that building. So who was it? Newton, force equals mass times acceleration. Your mass goes down, your force goes down. So you have reduced foundation demands, and also because the building is lighter, there's less gravity force pushing down. So when I say how does it compare, I'm comparing with traditional concrete and steel structures. How does the mass of these buildings compare? What sort of tonnage are we looking at? Obviously it depends, and I can only show you an anecdotal sort of comparison between the system. It depends on how far apart your columns are, what sort of flooring system you use, what sort of services you have through your building, and how much you're putting on top of your floor. But anyway, what we did is an example where we looked at an 8-metre grid, so a fairly open environment like you'd have in this room. We used a certain sort of precast concrete floor system called interspan, and we compare the different structures that we're looking at, concrete and steel combination, concrete by itself, and the timber structures that I was showing before in the previous slides. So what we see is that the key thing is that the timber buildings that we're looking at, which have effectively no concrete within them, are 40 to 50% of the mass of equivalent concrete and steel buildings. That'll have an impact on the foundation depending on what the governing criteria are in terms of the foundation performance, what the key issue is for the foundation performance. So for Christchurch, as Andy introduced before from Mishko's slides, there is varying layers of sand, silt, peat and underlying sandy gravel. So what we've got is many sites are going to exclude shallow foundations in the CBD, so sort of shallow concrete pads at the base. We can't really do that because of differential settlements. And that's what we've inferred from geotechnical reports that have come for a specific site that we were focusing on for the study. Now, that's not going to be the same all around. I emphasise it's not going to be the same for all around the city. So at our site was the old Café Valentino site, and this was the condition that we were looking at there. So at that site, the primary concern was limiting long-term, so that peat layer can squash down and cause long-term settlements, and also when everything turns to liquid, you can get settlements if you haven't got a foundation system that's founded on something hard. So what this means is that by reducing the building mass, it does have a big impact on what's going to happen with the foundation. You get a proportional reduction in the piles that you need for the reduction in mass that you get from the structure. So we considered 3 options, and I'll rush through this pretty quickly because it's a little bit technical, but we got one site, Café Valentino's, and we looked at 3 different options. One was to use a lightweight timber structure with standard piling technology, board concrete piles. Then we looked at using a standard superstructure and timber piles underneath. Then a lightweight timber structure and timber piles underneath that. Now this was the Café Valentino's site, and there was information provided by Di on this, and a geotechnical report by Geotek Consulting, and structural foundation designs by Constructure Engineering Limited. Now they did all the work on this, and we took their information and saw what the effects would be of using a lightweight structure. So that's the original design. It's just the floor as if there was no structure on it. So there's some concrete ground beams. This is looking from above. And then there's the dotted circular things of the piles which are going down. And there's quite a lot of 900mm piles. Quite a lot of, there's 1 or 2 600mm and 16 450mm diameter. So fairly large amount of piles that go into the structure. Now this was the building that had the $300,000 foundation for a 2-storey building. So it's quite a large component of cost for a 2-storey building. So option 1, with using a timber structure, what basically happens is that you can reduce all of the piles by size. So all of the 900s can go down to 600s, and all of the 600s can go down to 450s. So that's because you've reduced the mass of the building by roughly 50%. you can reduce that area of the piles. So that's how it looks. And then what we considered was again using some round timbers. Now you have sort of a limit on the size of those round timbers, and we chose what's called a short end diameter, which is at the bottom of the pile, because obviously as a tree grows, it gets thinner as it gets to the top. So that's the small end diameter. And that was 450 millimeters. So we considered that, and with that sort of design, we need quite a lot of piles, 98 piles. So what we wanted to do was present that, and I mean, you can infer from that figure that it's not really going to look like an easy job if you've got a heavy structure using timber piles underneath. Still, we need to look at the cost of that. It may be cost competitive because timber's cheap in terms of its round natural form, and you don't need to do much engineering to it to get it into the ground. So the third option was timber structure and timber piles, and here you get much less piles, 57 piles, and it's more evenly distributed, and it looks like something that's sort of comparable, I guess, to the original concrete design, but reduced. So a little bit about round timber piles. This was sort of a forest of piles because you drill down the first few metres and then you stand them up, and they're driven from that point on. Now this was a job that John Reelick here did in Auckland, and he'll answer any questions about it, I'm sure. So the key thing is when you're driving timber piles, it's not good for every site. There's going to be some particular sites in which there's some issues. And what can occur is if you're trying to drive through gravel layers, you can get splitting of these piles, so it's over driving of the pile. And what can happen in Christchurch is you might actually have intermediate layers of thin gravel layers that you need to shoot through in order to get to a thicker founding layer below. And so if you get this happening to your pile at that intermediate layer, it's not going to be a very good solution. Ways that you can deal with that is to armour the pile tip, put some steel on the end of it, and you can use water jetting, which distributes the fines at the base of the pile and allows you to improve the drivability of these things. There are a few issues with that as well, though. You can see that it's going to be pretty difficult to fasten these to the pile. There's a whole lot of number 12 wire wrapping there, and you might get damage to your jet pipe on the outside and the nozzle. I mean, you're driving through gravel layers, so there are some issues. One way around that is to put water jetting through the actual pile itself, and they've done that with precast concrete. And so bearing all those things in mind, I'll pass you back on to Mark to talk about our proposal for a timber pile solution.
Yeah, thanks, Mike. A few years ago, I had a little epiphany, should we say. I was considering the use of round timbers, and they grow naturally in a particular shape, round, for a particular reason. And if you don't process them, you still have a very strong element. In fact, they're the strongest they'll ever be when they're essentially in their natural form. One of the problems you have is the fact that when you try and treat them, radiated pine, we know if you don't treat it, is not particularly good if it's exposed to a wet environment. Problems with treating it, the treatment doesn't go all the way in, so you're left with a core of material that if you subsequently use it for a pile, you'll find sooner or later that the core section will rot out. And also we know if we use round timber out of the ground that there's inevitably in the drying process these big splits will occur in the round, and they can be a bit unsightly and also an avenue for decay of bugs or organisms to get in. So I thought, well, why do we need the core of the tree? It's only the juvenile wood, it's pith and it's soft, so how about we get rid of it? And so I spoke to John Reelick, the director of Tuakau Timber, and so he figured out a way to find a big termite to drill a hole up the middle of a tree. And so now we can produce timber that is 16 metres long with a hole in it. Now the advantages of that are that when we treat it, the treatment is also coming to the inside so we're getting full penetration on the treatment. So we don't have a core that is likely to decay with time. Also, when we dry it, we're drying the inside as well as the outside. So as you can see there, you haven't got any of those unsightly, splits that you can poke your ball pen in and things like that. And John can machine the outside as well. So if you want to, you can have a perfectly round, untapered member. So we thought we might be onto something here. John obviously thought so. They thought it was a good idea. And then, of course, with a hollow up the middle, you can then start introducing post-tensioning systems and concealed connections that are protected from fire and protected from the environment in terms of durability issues. With the situations you have in Christchurch, and we've been reinforced today with the geotechnical people who have spoken, that we have some challenging issues for your piles, for your foundation systems. And so it seemed that we could perhaps use this idea of a bored round member as a pile, and we can anchor the armour the tips of those for driving. Now we don't have to think about water jetting down the outside, and with these vulnerable water jets, we've got a hole up the middle. So we've got possibility now of using that process with a timber member, but not with the possibility of damaging the equipment. With the piles installed, there is a system called a Hitman, which is really just a frequency measurer which can tell you whether the pile is damaged or not in the driving process. And we could possibly even drop a camera down inside and have a quick look. Once the timber has been driven, we could also grout them, and that could have a benefit in that when we found these items on your gravel layers or whatever, those granular materials down there, we could infuse some grout into that material to reinforce it, which would give us a greater bearing capacity at the base of these piles. So here's just a bit of a schematic about how that might look. Now, this hasn't been tried. Okay, this is something we thought a couple of weeks ago. Now, here's something that may be useful in Christchurch. So we'd have to do a test, and I was talking to Anne McKenzie earlier, and she said, that's a good idea, let's find a site and we'll have a go. A question that has arisen is one of an environmental one, and what about CCA treatment and leaching into the aquifers that are below the ground here? Yes. Our copper chrome arsenic treatment, which is the preservative used that we know guarantees durability of Pinus radiata in the ground. There's 60 times more leaching of the treatment out of the end of a treated round than there is out of the side. You can imagine that the nature of a tree is essentially a bunch of tubes that the sap goes up and down this way. So when you treat it, you get the treatment very readily goes up the end grain, and of course that's where you get the majority of the leaching. So with the concept of grouting, infusing some grout at the bottom of the pile, we can essentially cap that off. So we would eliminate that the majority of the leaching which comes through the bottom, or we could in fact cap the ends of the members before we installed them. But also there's a possibility with the core inside, we could fill it up with grout, and you can see some reinforcing rods sticking out the top. We could do some things like locking it into foundations. If we're still concerned about possible leaching, the members can be coated, plastic coatings to eliminate that if it's at all a problem, and those coatings can come in any colour depending on what you want to see in the ground. Now perhaps, John, are you sort of there somewhere? Yeah, okay. Could you tell us a little bit about the amount of chemicals that are likely to be coming out of timber piles that have been treated?
All the chemicals we use are all natural chemicals that you'll find in the soil. There's a lot as background levels. So the amount that does leach out is in parts per billion, which is really, really, really small. So and sort of try and keep in perspective, if you had a meal of shellfish, just mussels or scallops, your arsenic level would really shoot up just from one meal. So what we have in here is it's very, very little that actually would come out. And if it does come out, it's only sort of maybe 2 or 3 inches around the pole itself. And that takes many, many, many years for that to happen.
Ground floor slabs. Now, the inspections that I assisted with early on after February, there was significant disruption of ground floor slabs with the liquefaction and the heaving of the ground, and you're familiar with that. So, how can we deal possibly with an alternative to a slab on the ground in a system that we might use like this? This is a building that we've modelled using the rounds, and Michael's mentioned he's run a number of earthquake records through that. So some years ago we had a project in the Middle East over a swampy area, and they wanted to build a roadway. So we had a look at the use of round timbers for that, and you can see here we have a substantial vehicle parked on that, probably more than the sort of load you'd get in your basement car park, and this is simply some options that may be worth considering if you want to have your ground floor just a bit above ground level, so if there's liquefaction, it can bubble up underneath and you don't have to worry about re-levelling anything. In this system, John at Tuakau, they have the equipment to nicely scallop all of these things. You can see the top of the piles all scalloped, so you get the headers in there, and so you can lock all these things together. So there are options that ensure you don't have issues with re-levelling afterwards, but that's something to sort of toss in the mix as a thought. I mean, this was designed for sort of heavy traffic loading, so obviously in your building you wouldn't really need anything quite as substantial as that, but it's an option. So some conclusions. Lightweight timber structures can significantly reduce foundation demands if settlement is an issue. Timber piles, we believe, are appropriate for your region, but again predicate that with the thought that a proper geotechnical investigation has to happen on each site because of the variability of the ground conditions. And we think that this idea of bored or hollow round piles has some merit. We think that we could utilise that to benefit. And I think I've just covered that. So there's cement grouting we can do. And there was some concern about lateral spread. You may have heard those terms used where the ground sort of does the horizontal thing. One thing about trees or timber is that it's reasonably flexible, so can accommodate some of those movements without modest amounts of movement without damage.
Robert?
Yes, I believe there's a new foundation code to come into effect next month. And I wondered whether that new code allows some vertical displacement of the foundations in a way that allows it to be jacked up again in the future. Is that allowed, or I'm a bit worried that
Well, to be honest, I haven't read that document yet, so
I'm a bit worried that the new code is not going to allow any movement at the time that you're talking about.
Well, certainly, I think the overwhelming advice that the geotechnical experts this morning gave us was that it's good to pile to some firm material. I mean, there may be situations where you cannot do that, and then obviously there has to be some alternative approach, which may be a raft type foundation or some other system. And I mean, Andy talked about some options there that could be explored. I don't personally know what the limitations in this new code are, or what the requirements are.
Robert, the Department of Building and Housing that writes the new rules, they are going to get some advice from this workshop that we've had today. They've asked for reporting from the workshop, and so hopefully we can assist in looking at what we need to do here. Okay.
Has anybody gone into the sustainability of the timber? Now, I know most of our timber's going abroad.
We'd like to hijack a bit of that and have it stay here, wouldn't we?
Definitely.
Okay. So let's have some more timber buildings. I mean, what we're talking about here is we've had one or two examples of timber buildings in New Zealand, but overseas they use them a lot. But we stick our logs on reamers and send them off overseas.
No, leave it here.
Okay. One question back.
What kind of plastic coating are you promoting to protect the pile if it's armour coated? What kind of plastic coating would be able to deal with the gravels that you're punching through?
We
John?
use polyura, and it's about sort of 3 to 5 mil I think.
Right.
But you actually mainly use that for out on the sea, for marine poles. That gives them an extra protection.
And that's been tested and found to be okay.
Yeah, it's about 75 years. They should last out in the water.
Another question over here.
I'm thinking of the combination of engineering and architecture here, and commercial buildings rather than privately owned. One thing that disappoints me is we've always lived with our 1970s concrete block buildings. Where's the opportunity to really bring some creative architecture to come alongside your engineering expertise, so we have a fantastic looking city that's the end result?
All architects, please stand up. One of the things that has been noticed as a result of the traumas you've suffered here is that regular structures perform better than irregular ones.
Okay.
Now, often creative architecture is perceived as being kind of a bit out there, sort of weird things that are happening. And, whereas engineers by nature want kind of symmetry, and so we're the structures perform better if they have symmetry as well. So I think you'll see probably less sort of out there architecture in terms of structural shape, but that doesn't mean that architects don't need to exercise their creative impulses to make your buildings look beautiful. I mean, we certainly, we do not want to see, gulags built around the place, do we?
Okay.
Is there any time frame on having approvals for your piles? Like, is it?
Well, I mean, timber piling has been around since Adam was a lad. All we've done is taken some rotting stuff out of the middle of it and put something better in, which is grout them or something. I mean, that's not an issue. I can't see that there'd be any impediment to, council approvals for what is a traditional building system, piles.
The question over here.
I think your hollow piles are a fantastic idea, and I've built numerous houses on the hills out of pile construction. However, with regards to the laminated buildings in general, how is that type of construction in particular going to get around the E2 clause in the building code with regards to moisture and so forth? I mean, we are at the moment battening all of our buildings, so we've got a cavity and things like that. Is all that type of thing going to be dealt with?
Yeah. Well, in terms of the treatment of the timber, I mean, we'll be treating probably to H1.2 just as a standard treatment for any internal framing, any internal members.
And externally?
Externally, we'd be talking H3.2, and then if it's in the ground, it would be H5. And so those levels of treatment can be introduced appropriately. We need to be in the timber. But in terms of the weathering skin, obviously that is a detail that we leave to our creative architects to deal with adequately. We're more into the bones of the building rather than the skin.
Our creative architects have created quite a few leaky buildings over the last year.
No comment.
As a creative architect, terrible timing. But yeah, no, you're right. But there's nothing in essence different from
the way that the timber structure works, and all of those examples, the timber is really internal, and then you're absolutely right that then it's down to us to make sure, and from the lessons that have been learnt in New Zealand from leaky buildings, to make sure that the outer skin is like that. And I feel very inspired by this, and it's a great opportunity to investigate the appearance of buildings.
Totally.
And I think it's nice to think that we can express that timber on the outside as well. So in the cladding, and that's so yeah.
Absolutely. One back there?
Yeah, I wonder if you're aware of the bridge in the Isthmus of Corinth, which is over 3 kilometres long, a suspension bridge where they have stabilised the 300 metres of silt below the ocean floor. The ocean is 68 metres deep where the bridge is, and they have sunk 30 metre long steel tubes into the silt, and they lie a metre below the top of the silt, and then they put gravel and a toboggan on each layer of 3 metres of gravel and built the bridge on top of that. As you talk about the rounds, would there be an advantage to them being hollow? And is it the hollowness of the steel tubes that is important, or would they stabilise the silt? There's been, I understand, 3 earthquakes. It's an earthquake zone. 3 earthquakes since the bridge has been built, of between 6 and 7.5, and the bridge has been fine.
Right.
We've got steel nets, so maybe
Right. Thank you.